In this video, we're going to finish up chapter P3, and we're going to talk about transformations of functions, even and odd functions, the zeros of functions, and also composite functions, where we put two functions together in an interesting way. Let's start off with transformations. Transformations are where we take a function, a shape that you may be familiar with, and we shift it around. We push it up, we push it down, left, right. Sometimes we even magnify it. We multiply it by something, and that stretches it. So I want to talk about the different ways of shifting your curve around or reflecting your curve. Let's use a function that you might be familiar with, which is your basic quadratic function. It's called the squaring function. Now, the graph of the squaring function is, I think, well known to you. It's a parabola that looks something like this. And there are a few things I'd like to do to that parabola. I'd like to move it around a little bit, up and down, left and right. The first translation will be up and down. We're going to call this a vertical shift. And this vertical shift by C units. This is the easiest transformation we have. If you want to create a new function, so we'll give it a new name, you take your old function and you simply, well, let's make C greater than 0. I want to make C positive. So if we add C, this is a vertical shift up by C units. If we subtract C, we take the old function, and on the outside we subtract C, and that's just a vertical shift down. So up and down couldn't be simpler. We're going to create one now. We're going to take g of x and make it f of x plus 2. Now, we know what f of x really is. It's x squared. So g of x would simply be x squared plus 2. Now, you already know what the basic graph of a parabola looks like, so there's no need to start plugging x values in and computing y values. Why not just take that curve and shift it up 2 units? Now, the vertex that used to live at the origin lives here. And then we can sketch our standard parabola-shaped curve right in there. And that's all that's going to happen. This is the vertex, and all we did was we shifted the vertex up 2 units. Now we can do the same thing by subtracting 2. We would move it down 2 units. So that is a vertical shift, up or down. Okay, now a horizontal shift. So if you would like to make a horizontal shift, and a horizontal shift will be to the left or to the right, once again, let's make C greater than 0. That means it's a nice positive C, and so we shift C units to the left or C units to the right, positive value. Once again, let's use our function x squared as our reference function, and let's create a new function, g of x. Now, instead of hanging the number on the back, you actually put the number that you're shifting right in the middle here. X minus C. And the thing about it is you see the minus sign and you would think minus negative, and you're probably going to think negative means over to the left. That's the negative portion of the x-axis. Actually works opposite of that. So x minus C is actually a shift to the right. But if we do this transformation with x plus C. And again, it's counterintuitive because plus C, you think the positive x-axis, you would think you're pushing it to the right, where actually, in this case, you're shifting to the left. So it's opposite of what you think. So let's shift this curve to the left or right. X squared is our standard parabola here, sitting right there in the origin. And now let's create g of x by taking the original function, whatever it is, and let's subtract 2 from it. Now that ought to be a shift by 2 units to the right, not the left. What does that look like algebraically? Well, function notation says we just replace the letter x with x minus 2, so we replace the letter x with x minus 2, and you can even square it out if you would like. But the picture ought to look like this. This is now our vertex, right here. So it's the same parabolic shape. It's just that we've shifted that over by 2 units like that. And it does go on forever and ever, of course. So just remember this one important thing about left and right. It's counterintuitive. If it's x minus 3 inside the function, it actually means shift to the right, which is counterintuitive. Keep that in mind when you're taking curves and transforming them. Now, we also have the ability to reflect curves. And the kinds of reflections we can undertake are these kinds of reflections. A reflection across the x-axis. And to do that, I guess all you really need to do is create a new function, g of x, which is the opposite in sign to the old function, f of x. That's all you have to do. So that example would look like this. And that curve would just be an upside-down parabola. So if you need to do a reflection across the x-axis, it's a matter of basically putting a big minus sign in front of your function. We can also reflect across the y-axis, and if you want to do that, let's get a curve that, see, if I reflected this across the y-axis, nothing would really happen because it's already a reflection across the y-axis. So let's get this curve right here. I'm thinking about f of x being the square root of x. You notice that this curve, the domain, is x is greater than or equal to 0. There's nothing happening over here because if you put a minus 1 in here, you get an imaginary result. So how do I reflect this across the y-axis? Well, this is what it would look like. Like that. So how do we create g of x? Well, it turns out that the way to reflect across the y-axis is to create the new function by not putting a minus sign in front of the function, but by putting a minus sign inside the function like that. That's a reflection across the y-axis. So what is g of x going to become? That doesn't seem right to me. How can we take the square root of a negative x? That's the square root of a negative number. Not exactly. Come on over here and take a look. We're over here at -3, -2, and -1. In fact, let's find out what the g of -1. How did I get this point right here? Well, the g of -1 is the square root of -x. And all is well. So, as you can see, we can do a number of transformations. Up, down, left, right. Reflections across the x. Reflections across the y. And how about trying to put the two reflections together? We call that a reflection across the origin. So I'm going to finish up by reflecting across the origin. What would that look like? I like this square root function because there's only that one little piece of it. What if I took the square root function and I reflected across the origin? Well, here's what it looks like. Every point you see here gets beamed across the origin and shows up over here. So this point over here beams across the origin. The origin is acting like a mirror, basically. And I'm getting a point way over here. So what is that reflection going to look like ultimately? Well, ultimately, the reflection will look like this. There it is. So this is a reflection across the origin. And I'll finish with that, at least on the transformations. All right, reflecting across the origin. Well, you need to reflect across both the x and the y-axis, so you need to do both. You need to take this new function and put a minus sign in front of the old function and inside the old function, both of them, inside and out. So what does that look like for our function? Well, here's our f of x again. It's the simple square root function. So g of x would be negative on the front, square root f of, well, that I replace x with negative x, and it almost looks like they cancel, but they don't. That's a reflection across the origin. Does it really work? Let's try it. See this negative 1 right here for x? It looks like that it's lining up with negative 1 for y. Let's try and see if it worked. The g of negative 1 is negative the square root of negative x. Well, that worked anyway. Negative the square root of 1 is negative 1. And again, all is well. We are where we're supposed to be. So now we can do all of those reflections. And in fact, we can even do a combination of those reflections if we want to. The next thing I would like to do is combine functions together. Now, there's many ways to combine functions. The easy way is to add them together. You can multiply them. The more interesting way is to combine them as composite functions. So I want to talk about combining functions as composite functions. Let's work on that. So let's say I had a function, f of x, which was equal to x squared. And I had another function, g of x, which was equal to 2x plus 1 or something like that. What I'd like to do is not add them together, but combine them in a more interesting way. I'm going to put the g function here and call it a machine, and put a nice little label on it, g. I'm going to have a conveyor belt in my factory, and on that conveyor belt is raw materials coming in. That's my input. And I think what I'll put in there, I'll start by putting the number 1 in. And so here comes the number 1 down the conveyor belt. The first thing it does is encounter the g function. It goes inside as an x, and what comes out the other side? Think about it. 1 goes in, a 3 comes out. Now the 3 continues down in this assembly line where it finally runs into another machine, a function. Machines and functions are the same thing. Machines receive raw material input, and they spit out output. Now, the input goes into G. What comes out is output, but we can rename it input because it's landing on the F function. So 3 goes inside the F function, and what comes outside? So 3 goes in, and a 9 comes out. Let's try that one more time. If I put a 2 in on this side, what comes out? This is G, by the way. A 5 comes out. So that 5 comes out, makes its way down the assembly line to the next machine, which is an F function that squares things. So 5 squared is, final answer is 25. Not surprised that we're getting perfect squares coming out of here, by the way, because it's the x squared function. So this is a composite function, actually. It is not the two functions working together algebraically by adding them. It's not the two functions working together by multiplying or dividing or anything else. It's actually one function working after the other. This is a composite function. And the way they're combined is with the word after. This is done after that. And the way we would notate that is like this. F of g of x. Now in the book they also notate it this way. F of g of x. Looks like fog, but it's f of g of x. I like this way a lot better. So everything starts here. Here's your input. Your input goes into the g function. G of x is computed. That's some value. And then that overall value is then finally put into the f function. So what we're really doing up here looks something like this. we're doing the f of g of 1. That's what's happening down below here. Now focus on g of 1 for a moment. Forget the f. What is g of 1? Well, g function's right here. The g of 1 is 3. Don't forget there's an f sitting out front. The last step is just finish up and do the f of 3. Well, f is squaring, so f of 3 is 9. So naturally, we do get the final answer, 9. Same would hold true if you put the 2 in here. We would actually get a 5 here, and f of 5 would be 25. But I have a question for you. How do we embody the two functions together into one expression? So I don't have to do the intermediate result. And I'm going to show you exactly how to do that. One-stop shopping, I call it. We want one expression that embodies the two functions working cooperatively together, one after the other. Here's how it works. I would love an expression for f of g of x. You cannot multiply these or add these and expect to get it. What you can do is the following. This g of x, the whole thing, is serving as input into this f function right now. In fact, if we don't want to be distracted, let's push the f of x function off the screen so we can't even see it. Now, if I said, actually, that's the wrong one. I think I need the f function, actually. The f function, that's what I need. So f of input, if I said, what's the f of x? You would say x squared. If I said, what's the f of 2? You would say 2 squared. If I said, what's the f of a? Hopefully you would say a squared. So what's the f of this ugly g of x thing? This is the one we want to eliminate. I don't want to see that one yet. Well, the f of g of x, you replace the letter x with this big ugly thing. So replace the letter x here with that big ugly thing. So instead of x squared, you get g of x squared. Remember, the way functions work is no matter what you put inside those parentheses, the letter x gets replaced with that thing. So I started by replacing the letter x just with g of x, just the letters or the expression g of x. Now we look at g of x and say, wait a second, g of x is right here. I know what it is. It's 2x plus 1. So I replace g of x with what we know it to be, and let's continue by squaring the binomial correctly here. So what is one-stop shopping? One formula that gives me the final result right away? It's this one. And again, you can't get that by adding or multiplying these. You really need to know how to composite them together. So let's go down here and let's look at our inputs and final outputs. This combined machine or combined function, composite function, when you stick a 1 in, you better get a 9 right out. When you stick a 2 in, you better get a 25 right out. Let's check it out, see if it works. Now, x just got replaced with 1, so all of these x's get replaced with 1s. And look what happened, guys. Out comes your 9. Now, remember, we tried this up in this diagram, and I put a 2 in. I got an intermediate result of 5. Squared up, I got a 25. When I stick a 2 into this combined function, I better get a 25 to come out. Let's put the 2 in and see what happens. So, 2 goes in here. Wouldn't that be 4 times 4? 2 goes in here. That would be 4 times 2, and don't forget the plus 1. What do we got here? 16, 8, and 1. 24 and 1 is 25. So this is a skill I think you need to work on and practice. If you haven't done it in a while, you really want to practice it. And it turns out that when you composite functions one way, you get a different result if you composite them in the other order. So let's try it in the other order. So a refresher here to remember that f of x was x squared by itself, g of x was 2x plus 1 by itself. And let's try it the other way around. G of f of x. Now this time I truly can cover the f function up, and I only want to see that g function up there because I know that when I stick things into the g function, it says my job is to double up your input and add 1. This right here is input because I put it inside of the g function. So g says, whatever you put in there, I will double it up and simply add 1. You can put anything you want in here. and it will double it and add 1. But hold on a second. F of x is well known to me. It's right here. It's x squared. So that's a completely different result from combining them the other way, and we will get different answers if we put a 1 or a 2 in there. So do take note that you want to make sure that you're looking at your composite functions in the right direction. Okay. So that's how to composite two functions together, something you really need to practice. Now I want to look at what are referred to as even and odd functions. Even and odd. And actually, even and odd functions have everything to do with symmetry. F of x equals x squared, that's an even function. Not necessarily because it has an even power, but it is a very nice connection that is an even power. Why is this considered to be an even function? The reason is because if you draw the parabola that represents y equals x squared, it is y-axis symmetric. So even functions are y-axis symmetric. Means that it's showing you that one part of the curve is reflecting across the y-axis. Now, we've also talked about this earlier on, and we've learned how to determine if a function is y-axis symmetric. And remember the test for this? That was to replace x with minus x and see if you get the same thing back. So let's replace x with minus x. Let's see what we get. I just replaced x with minus x here, so I have to replace the entire x with minus x there. But when you square a negative value, negative squared, negative 1 squared, you just get 1 yes. So we call this an even function. We've got another example of an even function. It doesn't have an even power, but how about f of x equals the cosine of x? From your trigonometry section, hopefully you remember that cosine loves to start at the peak. It goes down to 0, down to the minimum, which is minus 1, back up to the 0, and it keeps doing this, by the way, forever and ever. Boy, that looks y-axis symmetric to me. Okay, that looks like a perfect reflection. This is an even function. There's no even power needed. And there's a strong implication of that. And that is that if you were to replace x with minus x, it's the same as leaving it alone. And that is actually true of the cosine curve. You can try it yourself. The cosine of negative 10 degrees is the same as the cosine of 10 degrees. You can try it. Now, what about odd functions? I find it intriguing, again, that odd powers often lead to odd functions. But not all odd powers lead to odd functions, so you have to be careful. X cubed curve, it kind of comes down through here and then kind of goes out that way. This is an odd function. Now remember, not all odd powers give you odd functions. You really need to check it. What is an odd function? Origin symmetry. Do you remember the test for origin symmetry? You have to do both. Replace x with negative x and y with negative y at the same time. So here's our function, y equals x cubed. Let's do it. Replace y with negative y. Replace x with negative x. And let's see if we are right back to the same equation. So negative y. Now negative cubed, there's 3 minus signs. There's 1 left over. And then x times x times x. Divide both sides by minus 1. And we're right back to square 1. That is indeed an odd function which possesses origin symmetry. Don't forget how to check for origin symmetry. Just want to know another interesting odd function? Remember the sine curve? Sine curve loves to start at 0, go up to the peak, back to 0, and then down to minus 1, and then back up. But take a look over here. Doesn't that look like origin symmetry? this is definitely an odd function. And what that means, there's an implication here. That means that minus the sine of minus x is the same as the sine of x. That's another thing you can test, but it's true because it is an odd function or origin symmetric. Now, the last thing I'm going to leave you with is zeros of a function. They're really important in mathematics, and in particular in calculus. We end up looking for zeros frequently. Sometimes they're hard to find, but the one thing about zeros of a function, we have a good idea where they're located. If I gave you this function and I said find the zeros, now it would be trivial if the zeros of a function were x equals 0. That'd be trivial. The zeros of a function are the x values that actually make the y value 0. So what you're looking for when you're looking for zeros is you want to know when y equals 0. And which x values make that happen. Now, if you look at a graph, where is y equal to 0? Down here. So finding the zeros is synonymous with finding the x-intercepts. It's the same thing. So let's set y equal to 0. Now we actually have some work to do in terms of solving an equation. It's a quadratic equation. Luckily, that's factorable. So we'll go ahead and factor that. We'll set each factor to 0. And we've got our two zeros, 3 and negative 1. So not only are these zeros of this particular parabola, these are the zeros, they are also the x-intercepts. And of course, they're the solution to the equation. And there's even one more name for these things. They're the roots of the quadratic f of x. So zeros, roots, x-intercepts, they're all the same thing. Graphically, it's nice to know what the zeros are. They are x-intercepts. So oftentimes we are searching for zeros. We're looking for where the curve touches the x-axis. Sorry. No, that is true, the x-axis. So the x-axis is where y equals 0. Let's try one more example here. How about we have a function, like the example in the book is actually very good. Where would this touch the x-axis? Where are the zeros for this? Set y equal to 0, and let's find out. Let's factor this. Factor out the common x. That's the difference of two squares. Factoring really helps out here. There are 3 of them, 3 zeros, and I'm not surprised because the higher your power, the degree is the highest power of x, tells you how many zeros you could possibly have. Now, it doesn't mean you're going to have exactly 3 zeros. It means you can have up to 3 zeros. You could have 3 zeros. You could have no zeros, actually. That happens too. But you couldn't have 4 zeros, for example. Set each one of these to 0, and you have x equals 3 different zeros. Negative 1, positive 1, and 0 itself will yield a 0 or an x-intercept. Now, if you want to dig deeper into zeros, you might look at problems that aren't so easy, that aren't factorable. Now, if it's a quadratic and it's not factorable, you do have a way out. You can use a quadratic formula, and that'll spit the zeros right out. But what if it's a cubic function or a fourth function or a fifth function or something harder? We have something called the rational zero test. And the rational zero test, if there are rational zeros, meaning zeros that are not irrational, like pi or e or square root of 2, so rational zeros are zeros that are fractions or integers. If there exist rational zeros, the rational zero test will help you find them without even really factoring it like this. In fact, it'll help you discover the factors of the polynomial. So that's something for further study. You might want to look it up. But for now, we'll stick with these where you can factor them. That is all for this week. Make sure that you're staying on top of things. Last week, I know that by Wednesday, people really hadn't quite gotten to all the stuff, but you really need to be on top of the material online. So you want to make sure you're doing the reading, you're watching the videos, and you're doing the homework. Now, if you look at the beginning of each week, you're going to see when I'm expecting that each thing is done. So I'm going to be looking for that. I'm going to be expecting to come into class and just simply talk about these topics and have us all solve problems together. So please become prepared by staying on top of it. Thanks again, and we'll see you next week.